Click the bell icon to get latest videos from Ekeeda.
Hello friends, here in this particular video session, after completion of video session for comparator, we are looking for Schmitt trigger, that is one of the application of comparator circuit. In this video session, we will start up with case A of Schmitt trigger, that is inverting Schmitt trigger. This Schmitt trigger is basically open loop configuration with feedback. So even though we are giving the feedback, this circuit will work as a comparator. Okay. Now, second thing is, this is also called as regenerative comparator. This is because this will act as oscillatory signal. But hold on, the Schmitt trigger is not the oscillator circuit. Many a times in Viva session, people ask that whether the Schmitt trigger is an oscillator. The answer is no. This is because we are applying the input. But as far as oscillator concept is concerned, we are not applying any kind of input AC signal, but still we are getting the output signal, that too in sinusoidal in nature or faithful in nature. So here I will write one more point, that Schmitt trigger gives oscillatory signal, but it's not an oscillator, which is very important. It is not an oscillator. More specifically, I can convert any sinusoidal signal, rather any kind of signal, into the rectangular waveform, or I can say square waveform. Another namakaran for this is, this Schmitt trigger is also termed as square wave generator, provided I am giving V in is sinusoidal. If V in is sinusoidal, then we will be getting a square wave. Okay. Now let us understand the phenomena of Schmitt trigger. This Schmitt trigger is invented by Schmitt, and that is why we are taking this name namakaran as Schmitt trigger. Inverting Schmitt trigger tells you that here I am applying input to inverting terminal, and that is why a simple name of the Schmitt trigger is nothing but inverting Schmitt trigger. I am using this Schmitt trigger as name of regenerative comparator. This regenerative name कहीं तो सुना सुना सा लग रहा है, right? It is there in the oscillator, right? This oscillator is also called as a regenerative circuit. This is because we are giving positive feedback. Here we are giving positive feedback. As I mentioned earlier, that though it is open loop configuration circuit, it is the positive feedback. So we are getting positive feedback, mind well. Now we will draw the circuit in such a way that we are applying input to inverting terminal, right? And we are getting the square wave at the output side, and we are applying the input signal sinusoidal in nature at the inverting terminal. Moreover, I am applying the feedback at the non-inverting terminal. So let's see how this circuit will work. I am applying the input here. Nothing is there from this node. Only op amp, that is inverting terminal. I am applying feedback from non-inverting terminal through one resistor, that is, let's say this is R2, and one resistor is connected to ground. Let's say this is R1, and here I will be getting the output. Fine. So far so well. I am applying V1. Let us say that the input V1 is equal to A sine of omega t. It's nothing but A sine of omega t. The value of VO, initially we are considering that it is at plus Vsat. It is fluctuating in between plus Vsat and minus Vsat. This is because this Schmitt trigger is based on the operation of comparator circuit, and comparator is giving output voltage plus Vsat if your non-inverting terminal ka voltage is dominating over inverting terminal, and vice versa if your inverting terminal is dominating, VO is equal to minus Vsat. We will try to investigate what will be the value of the feedback, that is, let's say Vf. This Vf I can easily determine in terms of VO, but VO is changing, mind well. So as VO will get changed, your value of Vf will get changed, and this Vf, we will say that Vf is equal to, by VDR we can easily get to know that what is the value of Vf. Vf is equal to R1 divided by R1 plus R2. You can treat this as Rx Ry, no problem, नाम में कुछ है नहीं, into VO, and this is done by VDR, that is voltage divider rule. We will take this as equation number 1. We know that VO has two values. One is plus Vsat and another is minus Vsat. So we will say that if VO is equal to plus Vsat, then value of Vf is equal to, this constant term will be constant, R1 divided by R1 plus R2 will be constant, but just it will take the reverse order, that is and this I will treat it as upper threshold point. This Vf will become V upper threshold point, VUTP. This is nothing but your case number 1. Let's say case number A. Now we'll have to consider if VO is equal to minus Vsat. If VO is equal to minus Vsat, what will be the value of Vf? Then only the change is here will be minus Vsat. We'll be getting negative value. Now I can treat this Vf as, this is negative, so it's a lower threshold point, right? Rather than that, this UTP and LTP also have one name, that is upper triggering point and lower triggering point. You can take this as a threshold as well, no problem. It is working as the same as that of threshold and triggering, VLTP, and this case will become B. Now you may be wondering that why I am taking this plus Vsat and minus Vsat, case A and case B. The mind well, this is acting as an input. To get the output VO, I am comparing V1 and Vf. So if Vf is greater than V1, then automatically your VO will change. And in the next half cycle or in the next instant of time, we will be getting change in the value of VO. If VO is changing, automatically Vf will change, right? And again, your comparison ka result will get changed, and that will change the value of VO. So this gives the continuous change in your output voltage depending on these two triggering points. One is VUTP and another is VLTP. We will see this operation very shortly. Let us consider that I am applying V1 in such a way that this is sinusoidal signal whose maximum value is A and minimum value is minus A. And in between I will be getting VUTP and VLTP. So let us suppose we will consider that this is the level where I am getting the VUTP and this is the level where I am getting VLTP. This has to be less. This is because we are taking R1 divided by R1 plus R2. So it's obvious that your value of this VF will be less than that of plus VSAT or minus VSAT in the magnitude point of view. We will take this as VUTP. We will take this as VLTP. Very nice. So far so well. We will draw the output voltage in accordance with the case of comparison of VF and V1. Okay. We will slice this complete region into so many parts. First of all, we will take this region. Let's name this region as region A. In this region, what is the change in the difference voltage? Now in case A, what is the change in the difference voltage that I am looking for? Always and always this value V1 is less than this VUTP, and that VUTP is in one of the case it is nothing but VF, right? We will assume that initially we will be getting some value of VO, right? We will be getting some value of VO. Assume that VO is equal to plus VSAT at time t is equal to 0. At time t is equal to 0, we are having VO is equal to plus VSAT, so VF will become VUTP, right? So this VF is now VUTP, and now we have to compare the value of V1 with respect to the value of VF, that is nothing but VUTP, right? Now in A region, I am getting V1 which is less than the value of VUTP, right? So V1 case A, where I am getting V1 which is less than VF, which is nothing but V1 is less than VUTP. Fine, so well. Now if V1 is less than VUTP, your output will change, right? Initially at time t is equal to 0, it was plus VSAT. Now it will change. At this particular point, that is time t is equal to 0, it will change the output. So once it get to know that V1 is less than VUTP, then we will get to know that the value VO will become plus VSAT. So in this particular region, your value of VUTP, that is non-inverting terminal ka voltage, is dominating. So your value of VO will be as it is, that is plus VSAT. So we will draw this in this particular region, that is output voltage VO is plus VSAT. Okay. As soon as this particular region ends up over here, right? Let's treat this as point capital A. At point capital A, we will say at A, we will be getting V1 which is increasing beyond VUTP. That means inverting voltage is dominating now. Now I can say that inverting voltage starts dominating. As inverting voltage starts dominating, we will get to know that what is the value of VO. VO will become negative and negative VSAT. So there is a transition at point A with a value from plus VSAT to minus VSAT. So here I will be getting the value minus VSAT. Now there is a change of VF as well, because till point we have the value of VO is equal to plus VSAT. But at point capital A, we are getting change in the output voltage, that is plus Vsat to minus Vsat. So I will get to know that now VO is equal to minus Vsat. So Vf is equal to R1 divided by R1 plus R2 multiplied by minus Vsat, and that is nothing but VLTP. So Vf now will become VLTP, with which I will compare the value of V1. Now the value Vf is no longer as the value VUTP. Now we'll have to compare the value of VLTP. Right? Now we will take a region, that is B region, where the value of V1, which is greater than VLTP, from point capital A. So from point capital A to capital B, we will be getting the value of output voltage same as that of your previous one, that is VO is equal to minus Vsat. So we will draw here the value VO is equal to minus Vsat. Clear? Now what happens exactly at point B? Okay, we will consider case B, which is nothing but region B. In this region, your value Vf is equal to VLTP. V1 is always and always greater than the value of VLTP. Okay, and that is why we value VO is equal to minus Vsat, that is constant as that of previous one. Now we will come at point B. At point capital B. At point capital B, your value of the V1 is equal to VLTP and increasing towards negative side. That means actually the value of V1 is decreasing, right? So now as V1 increasing towards negative side, V1 will be less than VLTP. Now as soon as this V1 is less than VLTP, the comparator get to know that, oh, there is some change in the difference input voltage so as to change the output voltage. So I will say your output voltage will now become again plus SAT. Now there is a transition at point B from minus Vsat to plus Vsat. Are you all getting? Now I will change the value of the output voltage from minus Vsat to plus Vsat over here at exactly point B. So now at point B, my value of this VO is nothing but plus Vsat. Now we will consider up to which particular point the value plus Vsat will be constant, right? Now as VO is equal to plus Vsat, we will write as VO is equal to plus Vsat, VF क्या होगा? VF is equal to VUTP again. If Vf is equal to VUTP again, I can make a statement that this will change the comparison between V1 and your another terminal, non-inverting terminal ka voltage. This voltage is now become positive. So we'll say that V1 starts comparing with VUTP. And as till point C, we will be getting V1 which is less than VUTP. As V1 is less than VUTP, this VO will continue to have constant value, that is plus Vsat. And this will continuously change the value of Vf from VUTP to VLTP, VLTP to VUTP. And as soon as Vf changes, your value of VO change its value from plus Vsat to minus Vsat and minus Vsat to plus Vsat, same as that of earlier. This is how we will be getting the change in the waveform nature from sinusoidal to square wave. This is how I will get to know that this is the part of the square wave, and this will continue if I have the VUTP over here again. Then it will change its value from here, and it will continue to change its value again from minus Vsat to plus Vsat and so on. So till time t is equal to infinity, it will change its value from plus Vsat to minus Vsat and minus Vsat to plus Vsat. This seems that this is oscillatory signal, but mind well, I am giving input signal. Unless give input signal, we will not get any output signal, and that is why we are not treating Schmitt trigger as an oscillator circuit. This is how we have learned the operation of Schmitt trigger. Moreover, we have to learn what will be the change of the output voltage with respect to input voltage, and that characteristic is called as hysteresis characteristics. We will learn what is hysteresis loop. We'll draw a graph in such a way that this will give you the variation of output voltage, that is VO, with respect to input voltage. Now this input voltage is changing with respect to Vf, and Vf having two values with respect to plus Vsat and minus Vsat. Here I will take the value VUTP, and here we'll take the value VLTP. Okay. Now initially at time t is equal to 0, that means Vin is equal to 0. At time t is equal to 0, Vin was equal to 0, because omega t is equal to 0, sine of 0 is 0, so your value of V1 will be 0. So when Vin is equal to 0, your value of VO is assumed to be plus Vsat. If it is plus Vsat, we will name this as plus Vsat. This value will continue to have a constant value of plus Vsat unless I get the input voltage which is greater than the VUTP. As soon as I get the value of Vin is greater than VUTP, that means inverting voltage is greater than non-inverting voltage, then I will be getting VO is equal to minus Vsat. So at this particular point of Vin is equal to VUTP, there is sudden transition from plus Vsat to minus Vsat, right? Then if I try to increase the value again beyond the value of VUTP, the value will be constant, right? The value Vin will not go to infinite value, right? So we will be having a constant value, that is minus Vsat, up to point, that is maximum value, that is A over here. For our example, A was the maximum value for positive side. This is the variation of the output voltage with respect to input voltage if Vf is equal to VUTP. Now as soon as this VO is minus Vsat, now we will take this as minus Vsat. Now Vin will change its value from positive peak towards the negative peak, and as soon as it gets the change, and as soon as it overlap with the voltage, that is VLTP, new reference voltage, that is Vf is equal to VLTP due to minus Vsat, we will be getting the transition at VLTP, that is from minus Vsat to plus Vsat. So this is the direction of the variation of the output voltage with respect to input voltage. Now if again I try to increase the value towards the negative side up to the negative peak value, that is minus A, we will be getting same value, that is plus Vsat. And if I try to increase the value. Beyond this, this will be constant till I get the next threshold triggering point, that is VUTP, which is changed due to change in the output voltage from minus Vsat to plus Vsat. So this is looking like the hysteresis. This is called as hysteresis loop. Now loop A, B, C, D, which is getting formed with the characteristics of output voltage with respect to input voltage, is called as a hysteresis loop, and the width of the hysteresis loop is nothing but the change in the VUTP and VLTP. So this is called as VH. Okay, if in the numerical they ask us what is the width of the hysteresis loop, that is nothing but VH is equal to VUTP minus VLTP. Altogether LTP is negative value, so if Vsat is a constant same for both positive side and negative side, so this will become twice of VUTP if VUTP is same as that of VLTP as far as mod is concerned. So we will write if mod of VUTP is equal to mod of VLTP, then we will be getting VH is equal to twice of VUTP, and this is called as width of hysteresis loop. Cool. From the width of the hysteresis loop, we will get to know that what is the variation of the input signal with respect to your reference voltage, and that too depends on the saturation voltage. So far we have discussed about the inverting Schmitt trigger. Non-inverting Schmitt trigger is still left, so you have to stay tuned for further videos for non-inverting Schmitt trigger. I hope you like this video. If you like this video, then do share, subscribe, comment and like this video. Thank you so much.